Have you ever looked at a giant steel ship and just thought, how on earth is that floating? Well, a tiny little pebble sinks right to the bottom. It seems to defy logic, right? But believe it or not, there's a simple, super clever idea that explains the whole thing. And today, we're gonna uncover it. I mean, it's a total paradox, isn't it? A tiny little stone sinks. A colossal ship, weighing thousands of tons, floats. What is going on here? What's the big secret?
So think about it. You've got this little stone, sinks like, well, a stone. And then you've got this massive steel beast just cruising along. It's pretty clear the answer isn't just about how heavy something is, or how big it is. Nope, there's something else at play. A kind of hidden force, an invisible push coming right from the water.
Okay, so if we want to crack this paradox, our first job is to get to know this hidden force. We need to dig into this upward push from the water and figure out exactly how it works.
All right, so this force has a name. Scientists call it upthrust, and you've totally felt this before. You know when you try to shove a beach ball underwater at the pool, that crazy strong resistance pushing back up at you? Yep, that's upthrust. It's just the upward force that any fluid, like water, puts on an object that's in it. But, just feeling it isn't enough for science. We need proof. We need to be able to measure it. So how in the world do we actually see an invisible force? Well, turns out you can do it with a really simple but super smart experiment.
Okay, so check this out. First, we're going to weigh something just hanging in the air. Simple enough. Now watch what happens to the reading on the scale. If I push down on the object, the number goes up. Makes sense. But, and this is the key part, if I push up on it, the number goes down. See that? So here's the million-dollar question. What's going to happen to that number when we lower this thing into water?
And there it is. Look at that. The reading on the scale goes down. It's like the object just lost weight. And since we just saw that an upward push is what makes the reading drop, well, that's our proof right there. The water is literally pushing up on the object. Upthrust is a real, measurable thing.
All right, so we've proved the force is real. That's a huge step. But it's only half the story. To really get why a ship floats, we have to know just how strong is that push. And to get that answer, we got to travel way back in time, over 2,000 years, to meet an absolute genius from ancient Greece named Archimedes. So can we actually predict how strong this upthrust is going to be? Or is it just random? Is there some kind of rule to it all? This, my friends, is where things get really cool.
Archimedes cracked this with a super clever experiment, and we've got the data right here. Let's just focus on two numbers. First, the upthrust. That's the upward push we've been talking about. Second, the weight of displaced water. Basically, the weight of the water that got pushed out of the way. Now look at this. When the object is half in the water, the upthrust is 0.3 newtons. And the weight of the water it pushed aside? Also 0.3 newtons. Huh. Okay, now let's submerge it all the way. The upthrust jumps to 0.6 newtons. And the displaced water? You guessed it, a perfect match, 0.6 newtons. Are you seeing the pattern here? It's not close. It's a perfect match every single time. The upward push the object feels is exactly the same as the weight of the water it shoves out of the way. That's not a coincidence, people. That is a fundamental law of the universe.
And this amazing discovery is what we now know as Archimedes' principle. This is it. This is the simple, powerful idea we've been looking for. The upthrust is equal to the weight of the fluid displaced. That's the whole thing. And that one simple rule explains, well, everything. From why a leaf floats to why a massive supertanker doesn't sink.
Okay, we have the key. Let's go back and use this principle to finally solve our paradox once and for all. The best way to think about it is like a cosmic tug-of-war. You've got the object's own weight, right? That's always pulling it straight down. But at the exact same time, you've got the upthrust from the water pushing straight up. Whichever force is stronger wins the battle and decides if the object sinks or floats. So let's watch this battle in action. Look at object A. Its weight pulling down is balanced perfectly by the upthrust pushing up. It's a tie, so it floats. Now object B, same story. The forces are equal, so it also floats. But now, look at object C. Its weight is a hefty 2.4 newtons pulling down. The absolute maximum upward push the water can give it is only 1.9. So who wins? Weight wins, and the object sinks to the bottom. And this right here is the answer to our big question. If an object's weight is more than the upthrust, it sinks. That's our stone. But if the forces are equal, it floats. Now think about that giant ship. Yeah, it's super heavy, but it's also mostly hollow. Its huge shape displaces a massive amount of water, which creates an equally massive upthrust. And that upthrust is just strong enough to perfectly balance the ship's weight.
So, this isn't just some dusty old idea from a history book. Archimedes' principle is behind some amazing modern technology. Let's check one out.
Okay, so take a look at this thing. It's called a hydrometer, and it is basically just Archimedes' principle put into a glass tube. It's a super clever tool that's used to measure how dense a liquid is. It works like this. The hydrometer itself always weighs the same amount. So when you plop it into a liquid, it sinks just enough until it pushes aside an amount of liquid that weighs the same as it does. Think about it. In a really dense liquid, like super salty water, it doesn't have to sink free far to do that, so it floats up high. But in a less dense liquid, like alcohol, it has to sink way down low to displace enough fluid to balance its own weight. By just reading the little scale on the side, you can instantly tell the liquid's density. Pretty cool, right?
So there you have it. The whole secret behind the floating paradox is just this constant battle between weight pulling down and upthrust pushing up. The real question, though, is now that you know this, what else are you going to see differently? From a giant iceberg to a little rubber duck in the tub, or even just yourself floating in a swimming pool. Every time you see something float, you're actually watching Archimedes' big idea in action.